Hi there, grade 10s. I would like to continue our lesson on the historic development of the atomic model. We ended our session with Rutherford's experiment, and I just want to use the time to just conclude what he has said. So part of what he said was that from the scattering experiment was that the atom consists of a very small, very heavy, positively charged nucleus, and that he got from the observation they made from the fact that some of the alpha particles was reflected by the gold foil, and some of them were deflected as they moved through the gold foil. We discussed this in class, so the heaviness comes from the reflection, and the positiveness comes from the deflection, because helium alpha particles are helium-2+ ions. The symbol for alpha particle is that. And the very small comes from most of the alpha particles went through the gold undeflected. Right. So he said that most of the atom is empty space in which the electrons are found. By this time, they have already discovered the electrons. John Thomson discovered the electrons. And the protons are positively charged particles in the nucleus. This is what Rutherford said after they observed things I showed you in the video. Next guy is Niels Paul. He was a Danish physicist, and he suggested that the electrons orbits the nucleus in fixed energy levels. Remember yesterday we said that the Rutherford model couldn't explain why the electrons stayed away from the nucleus, because positive nucleus and negative electrons would attract. And this is not happening. Now Niels Bohr said that an electron can move to a higher or a lower energy level by absorbing or emitting certain fixed amounts of energies. And that's where he got the idea from, that the energy of the electron is quantized. And that is also why we represent the electron configuration like we did in grade 8 with the atomic model with the energy levels like orbits around the nucleus. And then in grade 9, we discussed Aufbau diagrams. So the idea of the electrons having fixed amounts of energy comes from Niels Paul. Right. Good. Some interesting personal information about Bohr. He enjoyed a Western movie. This was him as an old man. He said, everything we call real is made up of things that cannot be regarded as real because we can't see them. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Now, quantum mechanics comes from the idea that when you look at a particle and you see it in a certain space, or place. You don't know how fast it's going. And if you look at how fast it's going, you don't know where it is. Completely above most people's comprehension. So this is what we did in grade 8 to represent the atom. We had the nucleus with the protons and the neutrons in it. So the electrons would orbit, and the number of electrons would be equal to the number of protons. So this element is the element at the end of the third period. I guess you know which element that would be, because it's got a full third energy level. And in the nucleus, you have the neutrons and the protons. Right. Next slide, please. Now, these patterns of light we see here are called emission spectra. Now, Bohr discovered that each element has its own emission spectra. Now, these spectrums are formed when the electron falls from a higher energy state to a lower energy state. And then this frequency of light would be emitted by the atom. And the frequency of the light would determine its energy. And we can see here that hydrogen would emit 1, 2, 3, 4 visible colors of light. Now, light is part of the electromagnetic spectrum. Only hydrogen would have this line emission spectrum. So it's called the fingerprint of the element, because they can analyze the light coming from far or distant stars and objects in space and identify the element. Iron has more line emission lines, colors of light. So it means that there are more electrons, but also more energy levels. Very interesting. This is the line emission spectrum of iron. There's another one for hydrogen, helium. You can see each element will have its own frequency of light emitted. Helium, neon, sodium, and mercury. Line emission spectrum. You could see that none of those lines will coincide. The next guy is the famous Albert Einstein. It is said that he could hardly pass mathematics at school. I guess he was a bit bored. Einstein is one of the well-known modern-day scientists. He is best known for his equation E for energy is mass times c, that is representing the speed of light squared. And he discovered the photoelectric effect. And this effect is about light emitting electrons from substances. And it's the basic principle on which solar cells work. He also developed the theory of relativity, and he discovered nuclear fission. Max Born is the next guy on our list, and he was instrumental in the development of quantum mechanics. Later on in this presentation, there will be a video that, if it's possible, you can watch it in class on quantum physics. Oh, here it is. What is quantum mechanics or quantum physics? There is a video. If it's possible for you to watch it, please do so. The next guy is Louis de Broglie, and he said that electrons, and for that matter anything, has wave nature. So when something moves, it's got a degree of wave-like motion. and he suggested all matter would have wave nature. But specifically, it's important to know that electrons have wave nature. Here he's got an equation that he developed. This symbol here is the lambda, which stands for wavelength. The H is Planck's constant. The M is mass. And the V is velocity. We are not going to use this equation at school level, so you don't have to worry about it. But there are some things that you should get familiar with, like the symbol for the wavelength, Planck's constant, and velocity, as well as the symbol for mass. Right, some deviation from our atomic model. Next guy is one of my favorites, Schrödinger, Ernest Schrödinger. He thought about things quite a bit, and he was actually a mathematician, and he worked out the energies of electrons with mathematical equations. So he used mathematics to calculate the energy of electrons. Now, where Bohr had the idea that the electron orbited the nucleus, Schrödinger said, no, the electron moves in a three-dimensional space around the nucleus. And his mathematical equations helps us to see these spaces. They are called, these spaces are called orbitals. Here is another interesting video. It is called the Schrödinger's cat experiment, and you might enjoy watching this video as well. So here we have Schrödinger's idea of s orbitals. Where's my cursor now? So these very high density spots on the paper after the nucleus of the hydrogen atom says that the electron here is in the first energy level. Now it's all around the nucleus. It's not only on a flat space like in a hazy circle like this. The second orbital, also called an s orbital, is visualized by all these spots on the outer side of the first s orbital. These orbitals here are the 3 p orbitals. You always have 3 p orbitals together. They are the px, py, and the pz orbitals. If you take them apart, the px orbital will lie along the x-axis, the py orbital will lie along the y-axis, and the pz orbital will lie around the z-axis. And the shape of the orbital would be called lobe formed. They look like 2 teardrops tied together, or a long balloon squeezed in the middle. Right, these are the d and the f orbitals. You really don't have to worry about them. I'm only showing you the complicated shapes that these amazing mathematicians could work out. These are computerized visual images of the hydrogen atoms orbitals. This would be the 1s orbital. Better get a color that you can see on here. So this would represent the 1s orbital. This would represent the 2s orbital, 2s orbital, and the 1s orbital is there in the middle, and this would represent the 3s orbital. And here you'll have the p orbitals. And this would be the 3 p orbitals together. You've got them along the x, y, and z axis. I'm only showing you these images for interest's sake, to make the electron structure a little bit more visual in your mind. Next guy is Werner Heisenberg. He was another quantum physicist. He played a very key role, and he came upon the uncertainty principle. I actually mentioned that earlier. It's when if you know the place or the position of, for example, an electron, you wouldn't know how fast it is going. And if you know how fast it is going, you wouldn't know where it is. That is called the uncertainty principle. He was also instrumental in planning Germany's nuclear reactor in 1957. So I guess that would be one of the earlier nuclear reactors for generating electricity. Next guy is Clinton Davison. He discovered diffraction. Now, diffraction, the electron diffraction, diffraction is the bending. It's the bending of a wave around the edge of an object. Now, it's not difficult to demonstrate. You can take, now in class, you can take 2 pencils or your 2 fingers, put them very close to one another, very close, so that there's a very thin gap between the 2 pencils. And then you look through that gap at light, for example, the light in the classroom, or through at the light that comes through the window. And what you should see is you should see thin, out of focus lines of light and darkness. Now that is called a diffraction pattern. We'll discuss this later again. The next guy is Lester Germer. He said that light has wave and particle nature, so it could act as a wave as well as a particle. And for that matter, he pulled it through for applying to all matter. The last guy on our list is James Chadwick. Now we've got Democritus saying that everything is made up of indivisible atoms. We've got Dalton quite a number of years later that said the atom is indivisible and that it combines in fixed ratios, and he said every atom of an element is unique. And then we had Thomson that discovered the electron, and then we had Rutherford that discovered the nucleus. And in the meantime, they knew that, Rutherford said the nucleus contains the protons. And then we had Bohr saying there are energy levels in which the electrons are found. And then we had Schrdinger saying, no, not energy levels, orbitals. Now, nobody has mentioned anything about the other particle that also appears to be in the nucleus of the atom. It actually makes the nucleus double as heavy as what they expected it to be. And this is James Chadwick's work. He was the guy who discovered the neutron, which is the neutral particle, and it's got more or less the same mass as a proton, so it appears to be in the nucleus of the atom. So neutrons were discovered by Chadwick. Very interesting way in which he discovered it. If at all you have the opportunity, you can Google it and enjoy that. This brings us to the end of this session. The next video will continue on atomic structure. Thank you for watching.